Hello, everyone, and welcome to this episode of the Microsoft MakeCode Summer Learning Series for Educators. I'm so glad you're watching. Today, we'll be talking about troubleshooting and debugging in Microsoft MakeCode. Microsoft MakeCode is a free online computing education platform focused on students in upper elementary through to high school. MakeCode has three primary products: MakeCode for the microbit, which allows students to program the microbit, a small microcontroller device, and MakeCode for Minecraft Education, for students to code their own mods in the Minecraft game. And finally, MakeCode Arcade, where students can learn how to code their own retro-style arcade games. MakeCode supports both drag-and-drop blocks or text programming with JavaScript or Python. Everyone gets stuck sometimes, and it can be really frustrating. This is a GIF from a funny British comedy called The IT Crowd, and I can totally empathize with this. There have been many times that I've been so frustrated and angry that I've wanted to throw the computer out the door. But at these moments, it's helpful to remind yourself that when things go wrong or when you hit an obstacle, instead of treating it as a roadblock or as a failure, think of it as a great opportunity for learning. It's a mind shift, and you definitely have to remove the emotion from these situations. But I know the more time I've spent on a problem, the more I learn from it, and the more I will remember how to avoid that same problem in the future. Being a developer is all about problem solving. You can ask any professional developer, and they will tell you that the most important skill to learn is not about expertise in a particular language or framework. It's about knowing how to solve problems. And I love this comic here because it's so true. Whether the code works or doesn't, a programmer is essentially like a detective, always looking to understand what's going on and why things work the way they do. And technology is changing so fast these days that it's impossible to be an expert in something for very long, because next week it will all change. So, the most durable skill you can acquire is the ability to troubleshoot, debug, and figure out why it doesn't work and why it does. This is taken from a report that Microsoft Education put out a couple months ago that speaks to how to prepare students for the future of work in this age of AI. And it is coming fast. 1.3 billion AI agents are predicted to be in use globally by 2028. 50% of businesses are planning to use AI for their software engineering, and where it is enabled, AI is writing 40% of the code for developers these days. But this quote is actually from the engineering manager of MakeCode, Abhijit Chatra, who's been working in software development for over 20 years. He firmly believes that AI is not replacing developers in the workforce, but rather that the skill set of developers will change from writing code to owning outcomes, with a stronger emphasis on problem solving, evaluation, and quality. These AI tools are simply raising the abstraction layer. The job is shifting from developers being responsible for writing individual lines of code to owning holistic outcomes. So again, these core skills of problem solving, evaluating impact, and quality assessment are more important than ever. So in your classes, you can help shift this mindset from problems as a negative roadblock to problems as a positive challenge, and celebrate when something goes wrong because it presents a great opportunity for learning. The Computer Science Teachers Association, or CSTA, has just released the new CS Standards update. And part of these new standards include a set of student dispositions to foster. Problem solving and debugging directly correlate to dispositions of critical thinking, using logic to narrow down the problem scope. Persistence, trying different solutions. reflectiveness, thinking about how they might write the code differently, and resourcefulness, using different approaches to troubleshoot. And I love this quote from Winston Churchill: "Success is stumbling from failure to failure with no loss of enthusiasm." So the next time one of your students runs into an issue, let's celebrate it as a stepping stone to success. Okay, so let's use a framework for problem solving. The STEP mnemonic is a great one that I first saw as a poster in the back of an elementary school classroom here in Bellevue, Washington, and I loved it. It's a nice, simple way to outline the problem solving process. First, you need to say what's wrong or identify the problem without blame or bias. So, again, it's important to take the emotion out of it. I know that's easy to say, but harder to do. And I've been there, trust me, where I've been so frustrated by a bug in my code that I felt like steam is coming out of my ears. But in those cases, it's always best to walk away, take a break, do something else for a while, and come back to it with a clear head. Then, after identifying the problem, you can think of solutions, explore the consequences of these solutions, and then finally pick the best solution to implement. So STEP, STEP, say, think, explore, and pick. Now, I will say that in CS classrooms, most of your time will probably be spent here at the first step, trying to figure out what the problem is. Once you know the issue, usually these fixes are pretty straightforward. So let's go through each of these steps in a bit more detail. The first step of identifying the problem, there are a lot of strategies you can make use of. One of the most common strategies is to clearly document or describe what is happening. Something called rubber duck debugging is a very common practice in CS education, where students talk to a rubber duck and explain their code step by step to hopefully get a better understanding of what is going on. I myself think better when I write, so I like to write either in English or just pseudocode or even drawings, the program flow of execution. And at work, we use templates like this one to fill out bug reports in GitHub. If we run into an issue, we need to be able to clearly document what happened, the steps to reproduce the error, and any other details about the environment when the error occurred. Another first step strategy to identifying a problem is to determine if it's a semantic or syntax error. A semantic error is an error of meaning. So nothing's technically wrong with the code, but the program doesn't behave the way you want it to. For example, the program is running fine, but when you press the button, nothing happens. In this case, you want to understand what the expected behavior is and how that differs from what is actually happening. A syntax error is like a grammatical error in your code. So this is where your program won't even run or compile because something is wrong with how you wrote it, like you forgot a parentheses or didn't indent correctly. And in this case, you want to look at the error message to figure out where in your code is the problem. For syntax errors in code, there's a helpful tool in MakeCode called the Error Explainer that makes the default error messages easier to understand and points you to exactly where in your code you may have an error. This tool works for both blocks, JavaScript, and Python in MakeCode. Let me demonstrate. Here I am in MakeCode Arcade, and I have a project open that has an error in it. Notice that there is a problems pane that shows up at the bottom of the screen when there is a syntax error in your code. I can expand this error window to see more information about the error, and when I click on it, I can see where in the code my error is happening. But oftentimes, these messages may not be super helpful in debugging code. So we have a button here to give you the option to explain with AI. This does require you to be signed into MakeCode before you can use this feature. But let's go ahead and click on this. When I click on it, I get some nice natural language explanations of what's going on and call-out bubbles that show me exactly where in my code I went wrong. So here it looks like I'm setting the shell's position before creating the sprite. Okay, so make sure to create the sprite before using it. Now this feature also exists in our text-based editors. So let me flip over to JavaScript. And now when I click the Explain with AI button here, the explanation is displayed here in the Problems window. Looking at your code, you set the shell set position before I created the sprite. Okay, always create a sprite before you try to change or use it. That's helpful. So let's go ahead and change my code here. So I'm going to copy this this line of code and put it right after I'm creating the shell sprite. Okay, and that seemed to solve my problem, both in text and in blocks. Another strategy for identifying the problem is to try and narrow down the scope, so you can find the part of the code that is causing the error. A couple ways to do this is, first, try to comment out lines of code or disable blocks by pulling them out of their containers. This helps by reducing the amount of code that's being executed, so you can narrow down the problematic parts. Second is by rewriting your program to be more modular by using functions where possible. This is a programming best practice to separate out functionality and logic into different parts, helping to more easily navigate your program and identify where the problems are. And lastly, another way to narrow the scope is to use the version history feature in MakeCode. This allows you to see previous versions of your project, so you can go back to the last known good state. Let me show you how this feature works. So here I am in MakeCode Arcade with an open project that won't run. Something is wrong in my code. I've introduced a bug somewhere. I can access the version history by going to the Project Settings menu in the upper right-hand corner of the screen and selecting Version History. This will open up my project in a read-only view. On the right side of the screen, I'll see a pane with all the different timestamps and versions of my project. And I can click these different timestamps to go back to the previous version. Let's see, what version didn't have the error that I'm seeing? Okay, this is the last known good version. And then I can click to restore this version of my project. The next strategy for identifying the problem is to use the debugger. This is a powerful tool and something that professional developers rely on a lot. You can run the debugger for blocks and for text code in MakeCode. The debugger has two modes. The first is trace execution. This is where the code will execute very slowly and highlight each line or block of code as it runs. So we call it slow-mo. The other mode is to set breakpoints in code. So you can run the program normally, but as soon as you hit a breakpoint, the program will stop. And you can examine the values and step through the code line by line or block by block. Let's take a closer look at how this works. If you would like to follow along with me, import this link to a sample MakeCode for Microbit project in the MakeCode editor at makecode.microbit.org. This is a fun game that uses the microbit, where you try to line up 5 lights in a row by pressing the A button. It's very hard. Okay, I can't get it to go. But there is a subtle bug in this code, and it's a semantic error. So let me slow down the code so that you can see what's going on. I'll increase the pause duration here to, let's say, 100 milliseconds and see if I can line up the lights. Okay. Notice on that last column, I didn't actually need to press the A button to win. As soon as the light lined up with the others, I won the game. Now that's a bug. We want the user to have to press the A button for all 5 lights. So let's use the debugger to see what's going on in our code. To get into the debugger, click on this bug icon below the simulator. This will put your program in debug mode. This is a read-only version of the program, so you can't edit anything when you're in debug mode. And instead of the toolbox here, you can see that there's a debug window instead. And in here, you can see the variable values in your program as it's executing. The snail icon at the top here will run your program very slowly, in slow-mo, and the currently executing block will be highlighted. You can also set a breakpoint on code blocks by clicking the little circle on the blocks. And now your program will run until it hits the breakpoint and then stop. These buttons at the top of the debug window allow you to step to the next block of code and continue running until you hit the next breakpoint or restart your program. And then you can exit debug mode by pressing the button in the upper right corner. And debug mode looks the same for JavaScript or Python programs, with the addition of the step over, step into, and step out of code controls. First, let's look at slow-mo, or trace execution mode, to see what our program is doing. To start slow-mo, click on the snail icon at the top here. And here we can see our program running very slowly, with the currently executing block highlighted. So we can tell that this forever loop will run constantly to move these LED sprites down the screen. Now what happens when I press button A? Okay, so you can see I set the stop index here to a column value, 1. When I press it again, stop index gets 2. Okay. And then what happens when stop index is 4? You can see it jumps into this call check win function here. Okay, that's interesting. So now let's stop slow-mo by pressing the snail icon again. And now let's set a breakpoint to do a deeper dive. And you can click on these little empty circles here anywhere in your code to set a breakpoint. In our case, I want to see when we're calling this check win function here. So I'm going to set a breakpoint right here. And then in our check win function, I want to see when it's returning false and when it's returning true. So I'm going to set a breakpoint on both of these. Now we can run our program until it hits the breakpoint. So let's press button A to see if we can line up these lights. All right, and on the fourth click of button A, you can see that it does hit their breakpoint where it's calling this check win function. And I can step through here to see how this index is being incremented, actually all of my values. So stop index is 4, index is 1, and it goes through checking to see if these LED sprite Y values are the same. Okay, and it returns false, and then it continues to move the LED down the screen. Let's go ahead and continue running until we hit the breakpoint again. So here it's calling check one again, and then it's going to return false again because these lights aren't lined up. I'm going to continue running until they are. Okay, here is where it should return true. Yep, it does return true, but it does that and we win the game even though the user did not press the A button. So I think I know what's going on here. So let's go ahead and exit debug mode. And the problem is we're just calling the check when function a little bit too early. We want to call it on the very last stop index column. So I'm going to change this instead of greater than or equal to 4 to 5. So when stop index is 5, that's when we need to call our check when function. So let's see if that fixes our problem. So 1, 2, 3, 4. Okay, I'm not pressing the button. Oh, good. Okay, now I will. All right, great job. Good debugging. We've gone over strategies to help identify errors in code. So let's move on to the T in the STEP framework, and that is thinking of solutions. In this stage of the problem-solving process, it's always better to think of multiple different ways to solve the problem. And this is where getting multiple perspectives is great. This is a photo of some members of the MakeCode team at our daily stand-up meeting. And this is a time when the people on our team can share what they're doing and get everyone's thoughts and ideas on different approaches to solving problems. Once we have a list of potential different fixes, then we move on to the E part of the STEP framework, exploring the consequences and evaluating the impact of each of these ideas. Will the solution affect something else, like performance? Will it slow down our program? Or like security, will it open up any security vulnerabilities? And then thinking about the balancing of priorities of time, effort, and quality. Maybe the best solution takes 3 months to implement. If we don't have the time, then maybe we have to go with a lower quality solution that only takes 3 days. And finally, the last stage of picking a solution, implementing and testing. Testing is very important to make sure that the solution fixed the problem, but also that it didn't introduce new problems. This is a comic that shows the programmer responding to the question of, what are you working on? By saying, well, I'm trying to fix the problems I created when I tried to fix the problems I created, and on and on. And of course, you can always get help from the MakeCode community. Join the discussion at forum.makecode.com. There are a lot of MakeCode experts who participate, and of course, the MakeCode team also monitors the forum. So if you have a question or need help, you can post here. And just a note that this community is for people 13 years or older. In summary, here are the troubleshooting strategies we covered. First, document or describe the problem. Talk to the rubber duck. Identify if it's a semantic or a syntax issue. Use the error explainer for syntax errors. And try different strategies to isolate the issue, including version history. And then use the debugger. It is a very powerful tool. And finally, if all else fails, just ask on the forum. Here are some references that I covered in this presentation. And that's it. Thank you so much for watching this episode of the Microsoft MakeCode Summer Learning Series on tips and tricks for debugging. I hope you found it helpful.